Thank you, Dr. Ding, for volunteering to give this nice talk, or I think we're all excited to hear it, and I hope it generates some good conversation as well. So it's all for you.
All right, thank you, Jeff. My name is Ding Ziqing. I'm from University of Florida Lightning Research Group, and today, since it's Friday night, so I will keep my talk as short as possible, so people have different arrangement will have time to to spend. And my topic will be expanding high-speed optical observations of lightning processes from visible to infrared and ultraviolet range. Um, as many of you know that University of Florida, we do a lot of high-speed imaging of lightning. We have observational facility called Lightning Observatory in Gainesville. And in the past few decades, we were keeping imaging lightning using high-speed cameras and radio frequency measurement systems. So during my PhD, I mostly do several projects that focused on uh, high-speed imaging of lightning in visible, infrared, and ultraviolet ranges, and make extended our scope beyond optical and make infrared and ultraviolet high-speed camera imaging possible. So today, okay, nice one. Okay, so today we will discuss several questions. So first is, can we image streamers in different lightning processes, and how fundamental are the differences is between positive CGs and negative CGs? Second is the how lightning channel, including leader and return stroke, looks like in the near infrared range, and what can we learn from direct comparison of infrared and visible range images of lightning. So carrying these questions, so I would like to briefly introduce our research facility. It's we call it Lightning Observatory in Gainesville. We call it LOG. It sits on top of our new engineering building. It's a 5-story building, and as you can see, we have a 360-degree house, like a cupola, set in the middle of the roof, which houses all our high-speed image systems. Outside the cupola, we have the radio frequency field measuring sensors spreading out on top of the roof. We also have energetic radiation sensors, sodium diode X-ray detector. Inside the cupola, here we have different high-speed imaging sensors, and we also have some other imaging systems installed by other groups. So currently we have a total of 5 different high-speed imaging systems. Two of them operates in visible ranges, and one in the infrared range, and 2 in the ultraviolet ranges. They serves to imaging lightning at different framing rate, and also they have different field of views. And for the ultraviolet, we have the gating capability that can divide the frame, the exposure frame, into different sections for us to allow to control the luminosity, ultraviolet luminosity we imaged. Here is a picture shows the current configurations of all the high-speed imaging systems inside the log. Outside the cupola, here is the cupola, and outside it, we have different sensors. We have electric field measurement sensors. We have magnetic field derivative sensors. We have excuse me, we have X-ray detectors, and they also other different gains of antennas. So currently we use different algorithms to trigger the high imaging systems, and basically we use the radio frequency measurement systems to capture the waveform, field waveform of lightning, and use that to couple with the uh, the optical sensors signals, and then uh, uh, couple them together to trigger out into the other cameras.
So
Yeah.
will they trigger all the system at the same time or different device you have different trigger? Like
Trigger? Yeah, no,
yeah.
we used a homogeneous, the very same triggering algorithms. For different seasons, like for past few years, we use different ones. But for all the instrumentations, they were triggered under the same algorithm. So once you set up the same triggering, say, logic, then all the systems are triggered all at the same time, and they are all GPS time coded. Okay. So here shows the field of view of all the high-speed optical systems currently operating in log. The largest is low framing rate high mega speed camera, which operates at 1,000 frames per second. And all the others have a smaller overlapping field of views, but maximize their overlapped area in order to achieve the simultaneous observational capabilities of the same flash. Um, so yeah, next I would like to discuss several topics that I have or have not shown to the public yet. For the first one, it's called positive and negative lightning leaders imaged in ultraviolet and visible range. So this technically in this study we will compare what we observed using ultraviolet high-speed camera and the visible range high-speed camera. Talking about the ultraviolet, many different lighting processes amidst ultraviolet range. So in our study, we mainly image the near ultraviolet range, which is from 290 nanometers to 370 nanometers. Um, so the occurrence of corona or corona streamers, or in terms of streamers, there are different scenarios. Here are several examples showing the occurrence of them. And the first is um, here shows a 1.2 megavolts AC transmission line in Lyons, Oregon, and we zoomed in on top of the area that shows a Douglas fir tree, and in response to that transmission line of 60 hertz electric field, we can see the corona discharge at the tree's tip. Here we have a corona discharge from a human tent, which is really close, as 3 to 5 meters away from a jet-like cloud of negatively charged water droplets. On the most right-hand side shows adopted image from Kostinsky et al. 2018, I think. Shows a very short exposure of the corona streamer zone at the leader tip. During the step formation process. It's a laboratory long spark image. So some other occurrence of corona, including here, it's the corona discharge surrounding the barbed wire. We can see it's perpendicular emitting away from the center of that wire. And so the reason why corona streamer zone or corona streamers or just simply streamers happen is basically um, the moving charges interacting with its peripheral, which are surrounded by the virgin air. And when the charges moves inside the lightning plasma channel, there will be a leakage of current, and guided by the electric field, it will show as a streamer emission. So it's really hard to image those streamers because streamers mostly emit UV, and UV suffered a lot from atmospheric attenuation. And here I adapted plot from Reconcile 2024 shows how visible compared to UV that suffers from atmospheric attenuation. So as you can see at the distance of 5 kilometers, UV only have 22% left. And if we further increase the distance to say 20 kilometers, only 0.1% left for us to image. So in order to image UV, you have to be really close to the lightning channel. So yes.
Okay, can you this is so the percentage in the table is the remaining, right? Not the
Right.
not the absorbed intensity.
Yeah, so consider if you are image the streamers, which is emitting UV at 20 kilometers, you only have 0.1% of the original signal intensity.
Yeah, but the attenuation is also different for different storms, right? Because sometimes the range is harder.
Yes, you are absolutely right. For this calculation, it's only for the the atmospheric pressure that above sea level, and also there's no rain, no moisture and everything, so it's clear, clean air. Yeah.
Oh my God! If we have rain, so things will be different.
So if there is rain, your chance will be exponentially lower, because raindrops will absorb UV, including infrared and other bandwidths really, really badly. So yeah, even the visible, like if you have a wall of raindrops in front between your camera and the source, most of your visible light will be scattered, so it will be really hard to image, not even saying the visible.
Okay, thank you so much.
No problem. So yeah, in our lab, we use the ultraviolet intensifier coupled with a high-speed camera to image the UV emissions from lightning. And for the UV intensifier, since it's really sensitive and it has a really high gain, we use UV bandpass filter show here, and also a UV focal lens to achieve the best field of view for the UV high-speed image systems. So here I show some comparison of our observational records. On the top row, we show four frames of what we observed for positive leader, and at the bottom four is the corresponding visible frames observing the very same event. They are aligned, so the frame on top is corresponding to the visible frames on at the bottom. As we can see, when the positive leader approaching the ground, we observed we call it embellishment or enhancement at the leader tip, which is not observed for the corresponding visible frames. And we attribute that embellishment at the leader tip image UV to the streamer zones, because at the same time we cannot see such streamers in front of the visible in front of the leader in the visible range. And note that this is imaged at around 5 kilometers, and it's a positive leader. So positive leader streamer zone, it's more like a spherical spreading out compared to the negative, because negative we usually observed in the laboratory spark is usually not spherical. It's kind of bounded in different segments. And so we take a look at the UV embellishment in front of the positive leader in the regards of its width and length. So here is how we calculate at 90% luminosity level of that embellishment, and for all the frames we calculate all the width and the length variations as a function of time. And here shows the two dimensions. The first in red is the width of what I just showed here, and the length is perpendicular to the width of that embellishment. So with the leader, net positive leader propagating towards the ground as the time marches, the dimensions of both width and length of the embellishment are increased, and it's also experience the we call it variations in as a function of time. So the embellishment is not just stay constantly increasing, it's also changing in its size. So the ratio of the embellishment width to the channel width is we take the width here on the left and divide it by the normal channel behind it here at the tail of the leader tip. And for visible, because there's no embellishment, the ratio stays as 1. And for UV, it's also experience fluctuation with time. And we can see the ratio of the embellishment since the width is changing. So the ratio is also increasing during the propagation towards the ground. So since here we measured and observed the positive leader, how it will be look like in the negative, right? So here we showed in parallel the same format for negative step leader. On top, there are 4 UV images, and the bottom are 4 visible images. So as the negative step leader propagating towards the ground, we didn't see any UV embellishment at the leader tip, and the luminosity level for the leader tip and the channels behind it stays similar. And this is true also for the visible. So in short words, negative step leader didn't show much difference in the UV range and the visible range. And we didn't observe similar embellishment for negative step leader as compared to the positive leader we just showed. And we also took similar measurement for the ones that I just showed. Since we didn't observe any embellishment, this channel width near the tip didn't change, and also didn't vary much with time. So the increase at the later stage of the leader activities is because the scatter light. Also for the ratio, it stays as 1 for both UV and visible. So what about negative dot step leader, right? Will it show any embellishment? And what we observed is no, it didn't show any. Similar to the negative step leader, the dot step leader also shows a similar luminosity and sizes for the leader tip compared to the channel behind it. So in other words, we didn't observe any streamer in front of the leader tip for negative dot step leader. Here's the similar measurements showing no embellishment, and also the width didn't change throughout the time. So next, I would like to, since we just see how it looks different for UV and visible, now I would like to show some comparisons of negative lighting channel luminosity versus time in the infrared and the visible ranges. So here's just to give you a big picture of how return stroke looks like, return stroke channels looks like in the infrared high-speed cameras. And this is the picture imaged at 2.5 kilometers from the camera to the lightning channel plane, image plane. And This is a return stroke stage. The exposure time is around 1 millisecond. So what we do for this, yes.
Can I ask? So the exposure time around 1 millisecond.
For
1
you,
milli.
you mean
Yeah,
for infrared and visible?
like for each camera, can you tell me?
They are different.
The,
Yeah,
it's
for
different.
infrared is around 1000 frame per second, which gives you 1 millisecond interstroke interval. Oh no, in the interframe interval. And for visible, we have different. We have 1000 frame per second, which is 1 millisecond frame interval. And we also have another settings for 20,000 frame per second, which is around 50 microsecond frame interval. For the ultraviolet, it's a bit higher because we need to image streamers, which is more transient. For that, we have one UV image system operating at 49,000 frame per second, and another at 15,000 frame per second. So yeah,
the interval time, which is the time resolution, is different with the time exposure,
yeah,
right?
yeah.
Because for example, so the interval time should tell you the maximum exposure time, then you can change the
Sorry, I cannot hear you anymore after you take off the phone, the earphone.
okay, sorry, sorry,
No, it's
sorry,
good.
sorry.
Yeah.
Okay, yeah. So the interval time it just tell you the maximum exposure time, but then you can control the exposure time by yourself, right?
You are correct. Yeah, for the
Yeah.
UV you are talking about. So for the UV, so the maximum frame interval, that I just showed is 66 microsecond, but 66 microsecond. That is for the high-speed camera, and for the UV intensifier, we gated at 50 microseconds. So in other words, we're only looking at 50 microsecond inside that 66 microsecond frame interval.
Okay.
So yeah.
Yeah, it's so weird to me because your image is not saturated.
No.
Even like it's only 2.5 kilometer away.
Oh, you mean for this one?
Yeah, the distance, yes.
Okay, yeah, because for infrared it will never saturate.
Oh,
Yeah,
okay,
it's
for
have a
infrared.
much higher dynamic range, and
Okay.
in the middle of the channel it is saturated because you can see that so inside the channel, return stroke channel, its radial luminosity didn't vary much because the middle, the yellow part, it's saturated.
Oh, okay.
Yeah,
Okay,
but it
got it.
won't it won't cause scatter. I think what you mean is scatter because for visible camera during the return stroke, it will just all scatter like that, saturate your entire frame, right?
Yeah,
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 yeah.
because infrared emissions doesn't cause any scatter, so that's why it didn't blooming your frame.
Oh, okay, okay. So the infrared and the ultraviolet also.
The
Or
ultraviolet
only.
will cause scatter. Yeah.
Oh,
Yeah,
okay,
yeah,
okay,
it will.
okay,
But you can
okay.
control the gating in order to eliminate that artifact
Uh,
during the
oh,
return stroke. Yeah,
okay, okay. Thank you.
no problem. So we took a look at so for example, we took the cross section of the lighting channel for both infrared and visible, and here what we get. We show on the panel A is the visible range luminosity, the panel B is the infrared, and the panel C we compare with the electric field we measured. And we can see that for visible and infrared, it's really different because one thing is uh, here there are 5 return strokes, and visible luminosity will always decay to 0 um, between during the interstroke interval. So in other words, your after you have the first return stroke, there will be continuing current, and after continuing current, you will see no visible channel anymore until the next uh, dot leader return stroke happens inside that channel. But for the infrared, the luminosity will persist throughout the entire luminosity the interframe interval. interstroke interval, and it will never decay to a zero level, as you can see. Another thing is during that period of time, the infrared luminosity always show a hump compared to the visible that is just decayed to zero without showing similar features. So it drives us to think what caused this, the infrared hump, right? Because it's intuitive to think that the infrared always persists here during the interstroke interval because as long as the return stroke channel is still hot or have an elevated temperature, it will always stay there, emitting infrared emissions. But what is those hump? So we did some statistic analysis to what happened for both visible and infrared for the interstroke interval. We measured the peak current as a function, the infrared afterglow duration as a function of peak current to see if a higher peak current will cause a longer interstroke interval. And it doesn't show any direct correlations here. We also took a look at the number of preceding stroke to see if multiple return stroke will heat up the return stroke channel more and cause a longer interstroke interval. And the answer is still no. We also took at a number of M components during the continuous current after the last stroke to see if the incidence of M components which introduce more current into the channel, heating it up, will induce a longer infrared afterglow duration. What afterglow duration means is how long it persists after the return stroke. So we did find some correlations here. The more M components we have after last return stroke, a higher infrared afterglow duration will be. We also took a look at the correlation between the visible luminosity interstroke interval duration with the infrared interval. So the longer the visible luminosity interval is, the longer the infrared luminosity interval is. So what caused that hump? We just discussed. So because we saw that infrared luminosity hump always appears during the decay stage after return stroke. So we took a look at this plots adapted from Newman and Shaw from 1968. What they do is they did a simulation analysis on the temperature and also the radius of the return stroke channel and see how it cools down with time. And they found that at around like 3400 Kelvin, the lightning channel will take around 10 to tenths of millisecond to decay to a temperature of this 3400 Kelvin. And so we take that 340 we take a look at the plasma channel cooling processes at the atmospheric equilibrium of this. So this composition of air is what we usually have for the virgin air. And for lightning channel, when it cools down from 3000 Kelvin to 3400 Kelvin, we see that for nitric oxide, it will first increase and by 2 orders of magnitude, and then it will decrease by 2 orders of magnitude after this 3400 Kelvin. So which means that for infrared emissions, this nitric oxide is mainly responsible for that hump as compared to other chemicals or ions or other molecules inside the for the atmosphere. So next, I would like to show some basic lighting processes imaged simultaneously in visible and infrared ranges, and show some comparisons between the detailed frames of those lighting processes. So in this study, we imaged the M components after the positive return strokes, because during the positive continuous current, M components is not used to occur. And in this study, we found that as the consecutive frames showing here, during the continuous current stage, which is positive stroke, the currents of recall leader, which is bidirectionally propagated with negative end propagating upward and positive side propagating downward, after its connected to the continuous current channel, we observe a luminosity decrease inside the continuous current channel. And after its recall leader loses its connection to the continuous current channel, the luminosity starts to gaining back its luminosity back to the original level. And here there is the R2, means a second similar recall leaders happened attached to the continuous current channel, and it lose luminosity immediately. And after its lose connection, it will recover. The luminosity will recover back. Similarly for this, we have another horizontal recall leader propagating horizontally, and it attached to the continuous current via this attachment point. And then after that, we see the attachment, we see the luminosity decrease abruptly, and then recovering back after it loses its connection. So similarly in the infrared camera, not for the same flash, but also during the positive return stroke stage, after the return stroke, we measure the luminosity inside it. We also observe corresponding to M components measured in the electric field. We see luminosity increase for frame 1 and frame 3 in the infrared range. We also observe bidirectional transient during the positive leader stage in the both infrared and the visible range. So here we show the dynamics of these K leaders, or we name it bidirectional transients in this study. Their occurrence as a function of time, and here is the occurrence if there is one such bidirectional transient observed. We will show as an incident bar. And then we compare both infrared observation and the visible observation with the electric field, and we see them align well. Each K leader observed during the positive leader stage is corresponding to such a bidirectional transient happens. So how it looks like in real frames. So here are the visible range frames observed for those positive luminosity transients. It's initiate in a bidirectional manner and then propagating backwards following the previous created channel and connected to the parent channel. And after its connection, it will there is a development at the other side of the leader tip. We call it a new breakdown. And then this leader sequence will happen multiple times for the positive leader. Because traditionally we think positive leader propagates continuously, but in this study we found that it can propagating through luminosity transient. So here how it looks like in the infrared, since all the infrared channels can be seen.
So,
And
excuse me, what is the green color? So what is the green color?
Yeah, so
And
here are all the infrared images. So the green color corresponding to all the leader channels that happened before. And the black channels is what it's currently happens for the leader, but overlapped on the previous leader channels.
okay.
And the pink color means it is new. So for example, in panel C, we can see this luminosity, which is positive leader. It happens inside the remnants of pre-created channel, as here in green in panel B. And it overlaps showing a dark color, and for the tip of it, it shows in purple. So, which means in red, we see this luminosity transient follows the previous channel and also extended forward.
Okay, can I say the green color is step leader and then the black color is the dark leader?
I'm sorry,
I
can
didn't
you say that again?
So can I say that the green color is the step leader? So the leader of the first stroke, and then the black color is the dark leader. No?
No, it's not. So
Mm.
for A, B, C, D, E, all the panels here, it's the leader stage. There's no
It's le-
potential happen yet. So and this is positive. So so the green one is what happened before as a luminosity transient, and the dark one, the black one, is what currently have. So as you can see, so for the B, so this is the first luminosity transient. It happened, and then it will leave a ink here. So and then in C, this luminosity transient happened. It will leave a ink here as green in D. And same for D, will leave a ink here in E. So there are a total of 1, 2, 3, 4, 4 different bidirectional leader happens. So yeah, and then they happen intermittently. They are not happen continuously. So it's like they kind of retrace the previous created channel and make an extension and died. And then after several milliseconds, it will happen again, like a K leader. Yeah.
Okay, thank you.
Yeah, no problem. And so in F, we see the composite image of all the positive leader happened before, during that a roughly 300 millisecond interval. And then it looks really similar to negative step leader, right? But remember, this is for positive, and it's not happened at the same time. It's like intermittently happened. This is just accumulated in frames. So ironically, this positive leader didn't give a rise to a positive stroke. Instead, it will initiate a negative step leader here in this frame, and then give rise to 3 separate negative return strokes showing H, I, and J panels. So here is a cartoon shows how we observing both visible and infrared, show the dynamics of how this positive bidirectional transient mechanism is. So what we observed is just the bottom of this bidirectional leader tree. And each time there will be a bidirectional leaders initiate inside the remnants of previous created channel, propagating bidirectionally with negative side propagating upward, connecting to the parent channel, which is conducting, and the other side, which is positive, propagating downwards. After its connection of the negative end to the parent channel, there will be a reflection caused by the connection, and then facilitate the new breakdown at the positive leader tip. And then it will decay, and then the similar sequence will happen many times for that, for the positive leader stage. Next, I would like to show another interesting processes. We call it collision, imaging both visible and infrared ranges. So similarly, it's this flash is observed at a distance of 2.5 kilometers, and we will only look at this small regions and show the consecutive frames in the next slide. And maybe if you have noticed that I just showed this frame before, and this is the very same flash as shown here for the visible. And this is again for the infrared. This is 1 millisecond. And I also show 8 consecutive frames for the infrared from -8 till -1. And frame 0 is the return stroke as shown here on the right-hand side. And we can see that inside the 1 millisecond exposure, the infrared can resolute the temperature variation along the lightning leader channel. And then we can compare the luminosity of the infrared to the visible luminosity. So as promised, I showed the consecutive frames here in that small region, and there are a leading branch and the chasing branch for the negative step leader. And with the chasing branch approaching the leading branch, you can see in this frame, -17 collided into the side part of that leading branch. And after the collision occurred, the chasing branch is absorbed by that leading branch, and it will disappear, and the leading branch will keep propagating. In the infrared range, we see that the chasing branch connected to the leading branch with this here it's haven't been connected, and in the next frame it's connected. So you can see there's gradient in temperature with the leading branch and the chasing branch, and the and here on the right hand side also show the visible with accumulated frames with from -34 to -15, a total of around how many 17 frames to mimic that 1 millisecond infrared. So both shows the connection here, and in the infrared we can see the temperature. So here, next, we show a different region. We just now show this region, and now we're gonna jump into this region. Similarly, we see 2 active negative step leader branch collided with each other, and after its connection, one leader branch, we call it L2, disappeared and absorbed by this new formed leader branches. In the infrared, again, we see this 2 branches active in this frame, and in the next frame, this entire branch is absorbed by this L2. So another thing we can do for infrared range is we took cross sections of different altitude along the leader branch, and we measured the luminosity variation compared to the visible. And we can see compared to visible, we have similar luminosity variation for infrared, which means the visible luminosity, which is corresponding to the current, is similar to the temperature observed in the infrared. So we attribute this collision to the step formation at the front of the leader tip, because after each step for the negative step leader, there will be upward wave propagating upward along the leader channel, and it will change the electric field at different altitude of the leader channel, since the upward wave will be positive, while the inside the leader channel is mainly negative charges. So the positive wave will serve to attract the negative charges stored inside the nearby negative leader tips. So that's why the collision actually occurred. This is can proved by other observations by Wang et al. In 1990. They observed such upward waves in their dot step leader observation. And for here, we visualize each step as an upward wave along the leader channel, and that serves to neutralize negative charges inside the leader channel, cause those collisions to happen. So yes, that's all we have for today for different wavelengths and the blinding processes we observed. And if you have any questions, please bring it up, and I would love to answer. Thank you.
Yeah, so I have a question. Thank you so much for the talk, because
You're
it's
welcome.
really what it's really what I'm stuck right now with my result. So I want to ask you, yeah, because so you go back to the slide with the no, go back,
Go
go
here.
forward, go
Forward.
forward where you have the dark step leader.
Dot step leader.
Yeah, why do you call it dark step leader? Because they talk, or we call it step leader or dark leader.
Do you mean here, like
The last slide, I think so. The last slide.
here is the dot step leader. The last slide, okay. The last one, right?
Yeah, this one, yeah.
Yeah, for because so dot step leader is something between negative step leader and dot leader, because for dot leader the channel condition is still good, and it's remains very conducting, and in the electric field measurement we didn't observe any step pulses corresponding to the steps that is commonly observed in the negative step leader when virgin airs appear, and you have to break down the virgin air and then make propagation towards the ground. For that leader, since the channels is still warm and very conducting, and then there's no steps observed. But if the channel is not that well conducting, you will still observe stepped signatures in the electromagnetic field measurement. So that's why we call that step leader. It's something in between.
Dark leader and step leader. And then but you just say that when you observe step leader, you didn't see the pulse. So when you say you don't see the pulse, mean that you need to use the electric field signal, right? The
Yes.
fast antenna signal. So this means you need to compile with the fast antenna signal.
Right.
Like, yes. So and then at the beginning of the talk, you say that so for the step leader, we see the streamer
Right.
at the tip of the leader, but for the dark leader, we don't see that.
We don't see any. Yeah. So the reason why there is so here we observe the streamers, right? In front of positive leader.
Yeah.
Here for negative step leader, we didn't observe any streamers. And for negative dot step leader, we didn't see any streamers.
Yeah.
And for the dot leader, we also didn't, I didn't show here today, but we also have records for a negative dot leader. We didn't see any streamers neither. So yeah, and we think it is because the streamer formation for positive and negative leaders are different, because you require a much lower electric field to create a positive leader to develop as compared to negative. I cannot remember the actual numbers, but I think it's orders of magnitude difference. So that's why for a positive we always observe a continuous propagating for positive leads, while a negative is more like a stepping manner. And then streamers, since the streamer generation rate in front of the positive leader is continuous, So we have a higher chance of observing more streamer emissions in front of the positive channel, positive leader within the similar time slot. So as compared to negative step leader or dot step leader, you have fewer or smaller streamer production rate compared to the positive, because it requires a higher electric field to occur the streamers. So within a similar period of time of the camera exposure, you will have fewer streamers to observe from, and at a similar
Oh.
distance, and then you will have a smaller, have a fewer streamers to see.
Oh, it's really nice. Thank you so much for your
Yeah, yeah,
question, for your answer.
yeah.
Really helpful. It's really helpful because
Thank you. No
we
problem.
observe we observe the TGF that associate with dark leader, and we try to explain
I
why.
see.
So this is really useful. And
I see.
then
Yeah,
I
we can.
think
I
that this,
mean, we can discuss after this talk. I mean, now, and I also saw some TGF observations like sprites and other things. Because a sprite is it's called streamers, right? It's called streamers, and at
yeah.
higher altitude, you require so much less electric field for the streamers to happen, because pressure, the air pressure, atmospheric pressure, it's much smaller there, so it's easier to happen. And I believe for TGF, it's something similar because it's also higher altitude. And did you observe any UV emissions from TGF?
No, that's I'm going to ask you the next question
Oh,
about
okay.
UV. So
Yeah,
thank you.
please.
So can I answer this figure? I think you already published this result, right? It looked familiar with me. I think I read this paper.
Yes, we already
Yeah,
published. It's recently published,
recently published. Yeah.
like
Okay.
a month ago, like a month ago.
Yeah, yeah,
Yeah,
I think I read so. So I want to go. I want to go back, and now I want to ask you about the UV. So your
of course.
camera. So what is the range of the UV camera? Because in my group we want to buy want to buy a UV camera, but we didn't have money. So what kind of camera does you use for the UV or
So right
solar
now
cell?
there are different solutions. This
Mm.
UV system was built like 5 years ago. So at that time, there are no such solutions to image UV at high framing rate. So what we did is we use a phantom camera, and we use let me show you. So we use an image intensifier that coupled to the phantom camera behind it. Uh,
Mm.
so the intensifier is capable of doing high speed gating, and then
Mm.
we use phantom camera to image the image of that intensifier. So there will be a phosphor at the output end of the intensifier, and then you don't require a optical lens to image that. Um, but now I think for Phantom, if I remember correctly, they already have a existed solution
You.
for image UV, just solely,
Yeah.
yeah, yeah.
Just
Uh,
recently. Yeah.
just recently, what they
Mm.
do is it's similar. They have filters in front of their CCD, and then you just use UV lens in the front and to couple in the front, and then I think the CCD will then sensitive to UV range.
So the intensifier you make it in your group. So your group make it, or
No,
you
we
buy
bought it. We bought it.
bought
It's
it.
another company. There are several companies on the market that makes that intensifier. So on the right hand side, we use a GA Corona Finder. Um,
Mm.
and but for that one, it's a smaller gain. So on the intensifier on the left, which is this purple one, it's have a much higher gain.
Is this difficult? Is it difficult to make this system? You have the intensifier in front of the camera.
It's yeah, in the beginning it's really difficult. We put a lot of effort into couple them, and then adjust the focus. everything. It's
Mm.
very hard. And then after we get this UV2 system, we have a lot of experience already.
Mm.
And then it's easier for us to couple them together. And another thing about intensifier, it's really fragile.
Mm.
It's sensitive to temperature, it's sensitive to humidity, and also like the
Ah.
rains, exposure
Mm.
to the sunshine. Because
Mm.
it's super fast.
There's a lot of take care.
Yeah, yeah, and then the cooling is also a big issue here. Uh,
Mm.
but anyway, we make it possible. And also, like log is like greenhouse in summer in Florida. It's
Yeah.
90-degree Fahrenheit inside. It's a greenhouse. So you really have to think about how to cool the entire system down to
Mm.
ideal level. Um,
Mm.
yeah.
Very good. Well,
Thank you.
not to interrupt too much, but we are running out of time.
Oh, okay.
So and of course, you guys are welcome to take this conversation on. If you
Yeah.
wish to stay on and continue chatting, I'm going to log off. But Dr. Ding, you are a host, so
Yeah.
you when you log
Yeah,
off,
no. Okay, no problem.
Mm.
Yeah.
okay. All right, very good. Thank you,
Thank you,
guys.
Jeff,
Thank you, Dr. Ding. It was
for
really
making this
interesting
happen. I
talk.
really appreciate it.
No problem. And Dr. Nee, we will look forward to your talk next month.
Okay. Thank you so much.
All right. Bye
Yeah.
now.
Bye, Jeff.
Bye. Bye.
I can't figure out how to log off. All right. I hope it doesn't end the call. If it ends the call, you'll just have to chalk. Very good. There we go.
Yeah, so yeah, so a lot of issues to
Okay.
address. And also like the intensifier, the price is similar to the high-speed camera. So once you break it, it's really
It's the same, right? Then they just need to buy a camera.
yeah. So I think for this one, it's a T13.
Wait. Did he turn off the recording system? He didn't turn off the recording.
You didn't turn off?